I'm sorry?
On YouTube or on Zoom?
YouTube.
Oh, I haven't been watching on YouTube.
Okay. Zoom, I think they're pretty good quality, right?
Yeah, I checked the stream on the first day, and I could see everything just fine. Looks fine to me.
Yeah, I was more concerned with the YouTube quality.
I've checked YouTube and it's been good.
It's good. Okay. Yeah, sometimes I see that maybe a little blurry or not as defined as the Zoom video. I'm not quite sure how to improve the quality there. All right, let me share my screen. Share screen. All right, can everybody see my screen? Okay. All right. Yeah. So first, just a quick some administrative issues here. Let's see. Right. So if you go to Canvas, you know that you have here on the left-hand side. If you go to either Home or Modules, right, you have all the resources where I'm going to put some of the more common hyperlinks to things that you might need all throughout. You have obviously the syllabus, and which has all the entire calendar of the assignments and the exams. We also have Piazza. There's still going to be our main mechanism of communicating, so please stick to Piazza. We do have quite a few TAs who keep track of that channel, so and myself. So make sure that you always use Piazza as opposed to, I see some folks sending me messages on Canvas or email or whatnot. So it's harder for us to keep track of different communication channels. So if you could please, stick to Piazza. We also have links to the Zoom, if either to the section before this section at 135, or if you prefer at 325. And we're going to keep trying to make those two sessions be as identical as possible. But they'll stay more or less in line with one another. So yeah, so your choice, which one you prefer. Now, I did say at the beginning of the semester that the quizzes needed to be at that particular time and day for your section that you were in, and I'm going to backtrack on that. And instead, all quizzes are going to be available for 48 hours. So they'll be available the day that that they're scheduled for, in the morning or in the early mornings, and for up until midnight that day, and then again available the next day for another 24 hours. Okay, so a full 2 days it will be available. Okay, so that should cover everybody in all different time zones. No matter where you are. Hopefully you'll be able to take it on your own. Quizzes are meant to be done on your own. They are open book, so make sure that you make yourself familiarize yourself with the material, with the slides, with the assignments, with the videos. Go back and review all that before a quiz, and you should be fine. Quizzes are timed. They're about 30 minutes long, and you only get one chance to do it. They're usually about 5, 6, maybe 7 questions long. So I think 30 minutes, you should have plenty of time to answer that many questions. Again, it is open book, and you can access whatever you want. We ask you to please do it on your own. It is meant to measure your level of understanding of the material. The questions are random, so you might not necessarily get exactly the same questions from someone else. Again, to discourage folks from from copying from one another. You will they will be, most of the questions will be just fill in the blanks and multiple choice, so they will automatically grade. If you do have a problem during the exam, I would ask you to please take a snapshot of the question and then share with us on Piazza. In private, do not share it with other folks. And then we'll look into it when everybody has had a chance to take the exam. we will then deal with any issues that you might have had, and the answers will be made available after that, when everybody has had a chance to take the quiz. The lectures are available obviously in Zoom, which I believe are of a little higher quality. And I just wanted to see if I could, if you had had a chance to take a look at it and let me know if the quality is okay. If you have had trouble with passwords, hopefully you're not having trouble with passwords and you can access the videos just fine on Zoom. If not, they should also be available in this playlist, this YouTube playlist that I have for this particular section. And also, if you could, you can subscribe to my YouTube channel, and you'll get a notification whenever a new video is available. And on the chat, would you recommend taking the quiz after the class period on Fridays as opposed to before? Usually the material that we will be covering that day will not be relevant to that quiz. So it's really up to you whenever it's convenient. Usually the material that will be on the quiz will be being covered, at least 1 week before, right? So the next quiz I believe is on February 5th, and by that time we should have moved on onto other topics. The assignments are available here on the left-hand side, and they will be made available as we progress. And the quizzes are available here. So on February 5th, I believe that's when the first quiz will be made available. Please come to the quizzes, and you should be able to get started on that first quiz. And after that, after every week there will be a quiz. So on the 5th, then on the 12th, then on the 19th, and then March. Oh, maybe we have a midterm somewhere in there. But yeah, so there, go to the quizzes and you can take the exam there. What else? Let's see. Office hours are also available here, and I think this is a broad swath of days and times. Hopefully, you can find a time for you that is convenient to you for office hours. All right, let's see. Question on the chat. Do we need to use the workbench for the quiz? No, you do not need the workbench for the quiz. Well, that'd be nice. That'd be cool. At least for some of the questions, the SQL question, that'd be nice for you to have it. It'd be optional. You could use it for workbench, but you're not required. You won't be required to use workbench for the quizzes. All right, let's see. Where did we leave off last time? Let's see. By now you should have a working database running on your local machine. You should have a workbench as well. You can connect and do some queries and create tables and insert and updates and deletes. And we're going to be using that for the rest of the semester. We also covered this week. We started with database design, UML class diagrams, and we talked about the second assignment on creating a couple of simple class diagrams. We will be revisiting that and ask you to design some more. So the first assignment didn't cover all the design topics. We will be all throughout the semester. I mean, the whole course is called database design, right? So we'll be covering some topics here, the theory behind it, but really we will be practicing those topics all throughout the semester, right? But this first assignment in class diagram and design, it's somewhat simpler, but it'll get more and more challenging as we progress throughout the semester. Let's see. So we talked about the UML class diagram last time, and we get started in database data design, and I believe we almost were halfway through. Today we'll finish data design. Maybe we'll get to relational and constraints. Probably not. That probably we'll have to wait till next week. All right. So let's chat about data design. Let's see where we left off. Let's see. In data design, we we introduced the fact that it's hard to design databases just with plain tables, and we suggested that a better way of implementing is not to think about the database in terms of tables, but think about it in terms of classes, right? And the intention here is for us to be able to live in these two worlds, okay? Even though they sometimes are not perfectly aligned, right? The class diagram comes from the object-oriented philosophy that the world is made up of objects, and you have things such as inheritance, and you can classify objects into some fundamental classify in groups of things that are related to one another, right? So definitely this is a particular world, the object world, the object-oriented world, and then you have relational databases, right? It's made up of tables and relationships with foreign keys, primary keys, and so we want to be able to live in these two worlds and straddle between the two and feel comfortable of thinking about the data structure and how the data is structured in terms of classes, right? So we want our in our heads diagrams, but then when we are implementing them, we need to be thinking about tables, right? And oftentimes these translate very well. Classes can be translated into tables. Tables can be translated into classes. The attributes and properties in classes can be translated into columns and fields in the table, right? But not always, right? There's certain things that are peculiar about one world that are represented differently in the other world, okay? So for instance, here in the object class diagrams, we don't think about foreign keys and primary keys. Instead, we think about these lines and the multiplicity. That's what we think about, right? Usually we don't think about foreign keys and primary keys in this world. Instead, foreign keys and primary keys are something that is exclusive to relational databases, right? And that's why they're called relational databases, because you have these tables and you have records that relate with one another using these foreign keys and primary keys. And that's where the relationship, that's how you establish the relationship between tables, foreign keys and primary keys. Here in the class world, you also establish relationships, but you do that graphically with these lines, right? And then you establish how many are participating in that relationship with multiplicity, right? And we can convert one to the other. So we like to be able to think about the problem in the class world, but then always knowing that we're going to translate this into other representations. In particular, we're going to represent them in relational models, relational databases. Yes. Now you can represent them in other ways, right? You can represent them in object-oriented programming languages, right? Like Java or C#, or you can represent them in XML, right? Where you have a hierarchy of tags everywhere, right? Or you can represent them in JSON format, right? So there's an infinite ways that you can represent data and its structures, right? And we want to know, what are the mechanisms by which we can convert from one to the other and think about it in an abstract, really high level sense, but then be able to implement it in a concrete technology that we choose. Most of this course is that we're going to be mapping or converting these class diagrams into SQL tables, right? That's the bulk of this course, right? How to deal with it. But in the design process, we're going to think graphically, conceptually, but then implement it in relational models. Make sense? So we did spend some time on doing this, and we came up with a mechanism that allows us to go from tables to classes, right? And today we're going to go vice versa. How about if I have classes, how do I get tables, right? And we came up with a simple algorithm, right? This simple algorithm of 3 steps, right? That for every table, we're going to create a class. Right, so for instance, with this from this table, for each table we're going to create a class. So student, you get a student table, we get a student class. If we have a department table, then you're going to have a department class. If you're going to have a course table, then you're going to have a course class. Yes, and that makes sense, right? That's easy. Also, the attributes are also very simple. So if you have simple attributes, they, hello? Was there a question? No? Okay. Maybe it was a dog outside. Yeah, so all these attributes, name, title, right, years offered, the professor, the grad year, right, they translate to just properties, right, in the classes, right? But things such as primary keys and foreign keys, they don't translate blindly into the class diagrams. Instead, we know that these are particular to the relational database, right? Relational tables, right? That instead they convert in the class diagram as these lines, these association lines, right? And the multiplicity that specifies how many are participating. Make sense? Okay, so we went one way from tables to classes. We want to explore today going the other way around, from classes to tables. Okay. One word about yeah, no, first let's do this, and then I just want to present the topic. So first let's take a look at how is that we would go from classes to table. And so it's kind of like the inverse of what we did earlier, right? And we already can probably guess at some of the steps, right? So for instance, just like we said earlier that we were going to go that for each table, we're going to have a class, right? So a student table converts into a class. And for every course table that we have the course class, probably the inverse would be something like, for every class, we're going to have a table, right? So if you start off with a student class, you're going to have a student table, right? If you're going to have a section class, then you're going to have a section table. Okay, let's keep going. The same thing for the simple attributes, right? So for all the attributes, let's see, for the fields or for the columns of the table, basically they map to just the simple attributes in the class. So if you have a student name and year in the student class, well, then you're going to have a student name and year in the student table, right? If you have the department name, then you're going to have a department name in the table, and that, right? And then the relationships. Let's not get to that in a minute. Even though the classes are not going to have primary keys, right, and they're not going to have foreign keys as attributes, we are going to enforce that primary keys in the resulting table. So even though here we don't have a primary key for the student, we don't have a primary key for the department or the course or the section, we are going to start off blindly adding a primary key to each one of the table. Okay. Now this primary key can either be an artificial key or it could be a natural key. What do we mean by that? So by an artificial key, right? Something that, remember, primary keys are used to uniquely identify a record, right? So department, this would be the ID of some department. This is the ID of students, right? So this, we're saying that this should be either natural or artificial. What do we mean by that? By artificial, we mean that this is a field that has a unique identifier, but it doesn't necessarily map to anything, any reality in the real world, any physical thing that you can identify in the real world. For instance, we have student IDs, right? And the student ID is an artificial key, right? For instance, if you pay taxes in this country, you have a social security number. That is also an artificial key, meaning it's an attribute that is attached to your person, okay? But it doesn't match to anything real about me, right? It's an artificial number that somebody came up randomly and then it was assigned to me. Make sense? Something that instead, something natural would be something that might represent my identity, and it's something that we use in everyday life. Okay, people call each other by their first name, by their last name. Okay, so that is a natural use of an identifying feature about me that my wife might use, or my children, or whatnot, right? So for instance, this student name, right, could have been used as a unique identifier, for the student, as opposed to the student ID, right? Now, why didn't we use student name? Well, because can you guarantee that the name of a person is unique? Probably not. Okay, not in a particular context. Maybe even something that might look like it's unique, it might not be unique, right? So, for instance, in our section or in our course, maybe my last name Annunziato is unique enough to know that if it's Annunziato, it must be me. All right. But the bigger the context that you use, the less likely that the last name is going to be unique. Okay. And so we might say, well, what if you combine it with your first name? Would that be unique? Perhaps, right? That might broaden the context by which I might be unique. But there's no way for me to guarantee the uniqueness. So that's why here we didn't go with a natural field. Instead, we went with an artificial one. Now, that might not be the case for departments, right? In departments, we might say that department name, we might make a rule, right? That within a university, all departments must have unique names. Okay, so the name of the department might be, if that's the case, might be unique enough. We might have chosen department name as the primary key instead of some artificial ID. Make sense? I just want to distinguish what we mean by natural key or artificial key. Okay. Now for the weak strong and where you might have a one-to-many relationship, where you have a weak and a strong relationship, right? The way we implement that is that on the strong side, we definitely need a primary key, but we already established that everybody's going to have a primary key, right? So you already have a primary key. Now on the many side, we're going to implement that by having a foreign key referencing or relating to the primary key on some other table, right? So for instance, in here, we have the students having a foreign key to the department, the section having a foreign key to the course, okay, and so on and so forth, right? So that's how we implement the many-to-one or one-to-many relationship in the associations into foreign key and primary key. Make sense? So this might be the resulting set of tables after having been given a class diagram. And again, what I'm trying to drive here is that we should feel comfortable at representing classes as tables and tables as classes. That that even though there might there's not always a one-to-one mapping of something that you can draw, right, into something that you can actually implement, right? We still want to be able to conceptually think about tables as if they were classes. So sometimes you'll hear me refer to classes as tables or refer to as tables as classes, right? And so we want to blur the distinction between the two, right? And obviously knowing what limitations we have on either end, right? Limitations that we might have representing classes, or limitations that we might have on implementing tables. Yes. Okay. So, for instance, one of the limitations that we ran into early on was that representing many-to-many in a class diagram was easy. You just drew a line and you said star and star on both ends. Yes. For instance, you might say that a student is enrolled in a section, and that's all you want to represent. Then just a line and stars on either end. That's all you need. But if you're going to implement this in a relational database, that's not enough, right? You have to reify. You have to convert it into a separate table, right here, represented as a separate class, right? That has, instead of a single many-to-many, it has two one-to-manys, okay? And that is representable. That's implementable in a relational database, where that new table has foreign keys on the weak side, right, referencing the primary key on the strong side. Yes? Well, especially if you need additional fields, obviously. If you need additional fields, then you can't use the many-to-many here, right? You have to reify and convert it into an additional table with additional fields. Yeah, so natural key. So let's go and do an exercise at at applying this algorithm, we already went through the first step. We converted all these tables, these classes into tables, right? We already added all the primary keys. There they are. We already have the foreign keys referencing each one of the tables, correct tables, right? Major ID, pointing to the department, blah, blah, blah. Let's continue, and let's maybe pick out some natural keys and replace some artificial keys. Let's see, there's a question in the chat. Would the student class in the resulting schema have a department ID instead of major ID? Yeah, so the name of the field can be whatever you want. They don't have to have the same name. But definitely you need to be able to specify that what it is that you are referring to, right? And here we are not capturing that. For instance, I'm not telling you that this department ID is referencing this DID, right? I haven't said that. And major ID is references this DID, okay? Obviously, the actual implementation is that this is referencing that. For instance, there's a whole bunch of things that are not being captured here. I haven't told you that this is an integer or varchar, anything like that. So I would obviously have to capture it some other way. One thing that I would probably, what I'll do in the assignment, in the exam, do we prefer to use natural keys over artificial keys? If the natural keys are unique, yes. At least, as a first pass, if possible, right? We do prefer to use natural keys. Now, for performance reasons, we might decide not to do that, right? But that's a completely different discussion that we'll talk about later, right? But for design, right, when you are designing a database, yes, you would prefer natural keys as opposed to artificial keys, if possible, if it's unique. All right, so let's apply some transformations here, applying these principles. One of the principles is that we prefer natural keys to artificial keys. So for instance, here, instead of having a unique ID, if we can guarantee that the department is unique, well, then we're going to stick to the department name as opposed to having this unique ID artificial key, right? But this is going to propagate to other tables, right? Because we know that the student has major ID. We know that it's referencing the department ID. But if we're going to change that to be instead the name of the department, then we're going to replace this with instead the major name, right? And it's now referencing the department name. Other things that we might do is that, if we know this permit, we had initially created here a primary key that uniquely identified the permit. But if we know that this is going to be a one-to-one relationship, there's really no need to represent this, to have this primary key, because the student ID that we already had there, that was the foreign key that referenced the student for which this permit is, it's all, we know that it's unique, right? Because there's only one permit per student, right? So we could totally replace this permanent ID. We can replace it with a student ID being both foreign key and a primary key. Okay. Here also we had added a primary key initially to the enrollment. Okay, but if we know that we would want to maybe enforce or capture the fact that a student can be enrolled in a section only once, right? It would make no sense to have the same student enrolled in a section twice, right? So the combination of student ID and section ID needs to be unique, right? So that that combination could be the implementation of our primary key. So we could drop the initial artificial primary key and combine into a compound primary key. Notice the curly brackets here, right? That what we're doing is that we're combining the values of student ID and section ID. It could be combined as maybe a concatenation, right? The concatenation of both needs to be unique. And that's our primary key, the combination of those two keys. Here we had changed our department. Instead of department ID, we used the department name. So we're going here with the department name instead of department ID. Also, we might establish the rule that we say that course IDs or the titles of the courses need to be unique across the university, right? If we can accept that rule, then instead of having an artificial course ID, then we can use the title of the course as unique identifier, right, as the primary key. And if that's true, then the section which had a foreign key to the course ID that was over here, was pointed here, because we now change it to title, we can replace course ID by the title as being the foreign key to that section. Okay. All right, awesome. So now the algorithm has its limits. For instance, it doesn't consider weak to weak or strong to strong, but we'll revisit those a little later. All right, so okay, so how do we come up with that diagram in the first place? You know, why do we even start with this diagram? Right? Is this the best diagram that we can come up with? Right? How do we evaluate whether this diagram is any good? Right? And I mean, there could be an infinite ways of storing this information and the structure, right? So how do we measure whether a design is appropriate or it could be improved? So we were trying to make the point that any database design, the best way to go about it is to start with a conceptual diagram, right? A conceptual design using class diagrams. And so the question to how do we best design databases becomes how do we best design class diagrams, right? So a good class diagram hopefully will translate into a good database, right? So how do we come up with a good class diagram? Okay, so these are some very generic, very high level steps on how is that you would go about designing a good class diagram. So the first step is the most important step. So the first step says that, well, you have to gather requirements, right? You have to come up with some requirements document, okay? And if you've taken OOD or you've taken other design classes, you might have discussed in there that projects are most vulnerable at this phase, right? Coming up with the requirements, meaning agreeing amongst ourselves what it is that we're going to build, right? And humans are flawed, humans are we're messy, and our language is it can be very contradictory. It can be have many different interpretations, and we might have egos. We might have some political differences. We may have all sorts of bad things, right? That don't allow us to come together and agree. And so the coming up with the requirements is the most vulnerable part because it involves dealing with folks, dealing with people. Okay, and you ask one engineer what it is that we're building, and they'll tell you something, and you ask a different engineer, and they'll tell you something else. and so how is it that we reconcile all these differences, right? If you ask the owner, he might want to do something. If you ask an HR, they might tell you something else. Engineering might tell you something else. Sales might tell you something else, right? So how is it that we can reconcile all these points of view? So definitely that's the weakest part of these steps. Hopefully, by the time once you come up with a good set of requirements, then we need to convert that into a class diagram, right? So this part is not as hard. Right? This is the easy part. Converting requirements into a class diagram, that's easy. Coming up with requirements, that's hard. So if you first start off with once you have the requirements, you convert that into a preliminary class diagram that you are going to refine over time. Okay. And the first pass at coming up with that class diagram is to try to identify all the nouns and all the verbs, right, that we find in the requirements. The requirements are going to be full of nouns, full of verbs, right? And those are going to be transferred into the class diagrams as classes. So nouns are going to be converted into classes, and the verbs are going to be represented by the associations or the relationships between the classes. So the nouns are going to be the boxes, and the verbs are going to be the lines. Okay. So you first come up with a very an initial approximation of what that class diagram might be, and you're going to iterate over over time at making it more and more mature. Okay, you're gonna start looking for inadequate relationships, right? Relationships that shouldn't be there. Okay, maybe you're missing a relationship that should have been there, or you put a relationship that should not be there. Okay, or you thought that these two were related when it's actually these two, right? Or maybe you thought only two things were related when really there are three things that are related, right? So we need to identify these relationships. We also have to identify redundant relationships. Redundant relationships are those relationships that allow you to answer certain questions in multiple ways, right? Where you might have one question, but you can answer it either relating to classes, or you can answer it by relating these to other classes, right? Or maybe three classes, right? And we want to avoid redundancy because redundancy breeds inconsistency, right? And what we mean by that, I always use the analogy of having two clocks, right? And even though you look at the two clocks, look at over here, it says 7 a.m. and this one says 7 a.m. And logically, they should give you the same answer. If you ask either one, right, they should give you the same answer. But inevitably, it happens for whatever reason that these two data storages might drift apart from each other, either intentionally or unintentionally. And now whenever you're going to ask the question, what time is it? One of them is going to say one thing and the other is going to say something else, right? So this inconsistency of the data diminishes my confidence on the data source, right? Now I don't believe either one, right? So inconsistency, if you ask one query and says how many products did we sell last year, and it comes out to be 1 million sales, and you ask it some other way that logically should give out the same answer, and it comes out to 1,200,000, it says, wait, which one is it? Is it one or the other, right? So now you diminish the value of the data storage because of these inconsistencies. So definitely we want to eliminate redundancy wherever possible, right? Because redundancy breeds inconsistency. We're also going to revise strong and weak relationships, since we need to reify them and convert them into something that can be implemented in a relational database. We're also going to revisit the attributes, things that might have decided then to be classes should have been actually attributes, or things that we made attributes should have actually been classes. Okay, and then we're going to apply these steps 3 to 6, over and over and over, revisiting this class diagram, condensing it and making it smaller and more concise with only the classes and relationships that actually need, right? So this process is non-trivial, but it's definitely easier than the requirements specification. This course does not cover requirement specification. There's a whole course on that. OOD probably covered that. This class deals with this set of steps down below. All right, so just a brief word on requirements analysis. Basically, it involves a slew of interviews with the stakeholders, with the owners, with the folks for whom you are building the database, right? You're interviewing them, you're asking them questions, and in these interviews they might ramble on about stuff that is irrelevant to what it is you're building, or they might give you very valuable information. Okay, and you as the interviewer, right, you're going to be jotting down all these conversations. Also, you might be looking at all the forms that folks are filling out, right? All the data entry. Also, you'll be looking at what kind of reports are they generating over time, and see, okay, well, the reports will give you a good clue on what kind of questions the system needs to answer, right? Is it how many products were sold? What are the trends? What trends about competitors, about the market, right? All these kinds of things, your database is now going to need to be able to answer, right? So these questions that you want to be able to ask the database are fundamental for the design of the database, right? And so all this goes into a requirements document, right? And that requirements document is the beginning for our process of designing the database, right? So here's an example of what an interview might have come up with, right? You're interviewing your employer, your clients, and they might be describing a university, right? They might say, the universities are composed of departments, academic departments, such as mathematics and drama. They offer different courses. You have non-academic departments such as admissions and dining hall, right? They are responsible for other tasks for keeping the university running. Notice that perhaps the academic departments offering courses, probably that's very relevant to our application, to a database that we want to implement. But probably this information about non-academic departments and the dining hall and other tasks running the university, that probably is completely irrelevant to the database that we want to build. So, you as a data engineer, right, need to be able to filter out and say, well, what are we building? Right? Are we, this is some of this info is completely irrelevant. As you keep reading, you'll find several nouns, like students and years and majors and courses and sections and professors. And you'll find also different verbs, such as enrolling, right? Or that it has one or more, that it can be taught, right? All these verbs, right? And nouns, you want to create a data dictionary of all these things are listed, right? Here's a couple more. You have that each student is allowed to have a car on campus and they need a permit, right? And the permit is going to list the license plate, the model of the car, right? And some of the questions that the database needs to answer, or allow folks to do, they need to allow students to declare their major. They need to keep track of the permits. They need to allow departments to specify the sections and the course that they're teaching, allow current students to enroll in sections, to professors to assign grades, right? So these are all the different things and requirements, in nice, neat requirements document that is going to drive the design of the database. All right, so the first part is that we read these documents, right, and we create kind of like a data dictionary of all the nouns and the verbs and how they relate the nouns in a data dictionary. And we are responsible for maintaining this data dictionary. Things such as university and course and student and year and grade, all these are the nouns from where we read just in our specification. Now, we're also responsible for making sure that if you might have two words that mean the same thing, right? That might be alias of each other, right? Some folks might refer to folks as clients. Some other folks might refer to the same as customer, right? And they mean the same thing, right? And it's your responsibility to capture these kinds of things in a data dictionary. You might also capture nouns such as composed of, offers, has, graduates in, majors in, receives, assigns, right? Now, most of these verbs will be relating to nouns, right? So professor assigns grades, right? A professor teaches a section, right? A student enrolls in a section. A student receives a grade, right? So most of these are binary relationships, right? But not always. You can have, not only verbs do you care about, you also might care about verb phrases, right? Where you might have not just one verb, but multiple verbs, where you have multiple nouns, not just two nouns, but maybe three nouns or maybe four nouns that need to be related to one another, right? So you need to keep track of all these things as to come up with a preliminary class diagram, okay? Now, it's also your responsibility to make sure that, filter out any nouns that are irrelevant, right? And also make sure that that you know what the scope of the project is, right? So, for instance, identify that what it is that we're building, what it is that we're not building, right? We're not building anything for employees or maintaining the finances of the university, and also the granularity by which you want to capture certain information, right? For instance, you want to capture information about a car, You might care about their license plate, right? And maybe the make and model of the car, right? And maybe the color of the car, but you don't care about its light bulbs or the upholstery, or how fast can it go, maximum speed, or you don't care about those things, right? So it is your responsibility to filter out what's relevant and what's not relevant, what's scope and what's not scope. Okay, it's also responsibility of trying to visualize the tables that you might need, right? For instance, we need to keep track of a whole bunch of faculty. Maybe we need a table that keeps track of faculty, or a table where we're going to keep track of a list of all the courses and a list of all the departments, right? And for instance, not all nouns need to be represented, right, in the database, right? For instance, the noun of university keeps popping up, right? So you might think, oh, well, maybe we need a table that keeps track of all the universities. But Sam said, wait a minute, what all universities? We're only implementing one single university. So it might make no sense to have a table of universities because there's only one of them, right? If this were the Department of Education, then yes, maybe you do need to keep track of multiple universities, right? And so you do need a table for universities. But so that's your decision, right, on whether you need it or not. Okay. So taking all this into account, you might come up with this initial class diagram, right? This is a first go, right, at what you think this class diagram might look like, right? Where you have students, grades, departments, professors, sections, all the important nouns that you might have captured here. They're represented here as boxes, okay? And all the verbs of majors in, enrolls, receives, assigns, teachers, right, are represented here in the lines, right? So a student enrolls in section, a professor teaches a section, a professor assigns a grade, a student receives a grade, right? Yeah, so this is the beginning of the class diagram. We're going to iterate over this class diagram, making sure that there are no redundancies, that there are no inadequate relationships, right? And making this a better class diagram. All right, let me turn on the light here. Okay, so let's take a look at the steps that we just went through, right? So we went through the preliminary class diagram, right? And the nouns and the verbs of the specification. Let's go on to take a look at the relationships. In particular, we're going to look at for inadequate relationships and redundant relationships. Okay, so let's look at first inadequate relationships. Okay, so relationships, they describe, how entities, and by entities we mean it's just a fancy word of things that are going to be stored in a database. Okay, it's a fancier word for records. It's a fancier word for classes or objects or tables, right? So it's a fancier word. It's something that we are going to store, and so it's a data point in a table, in a database. Yes. So relationships connect data points. Yes. So for instance, this student from this class diagram, we see that the student has many relationships. It is related to department through the majors in. It is related to grades through this receives. It is related to sections through this enrolls, right, or graduates, or is issued. Okay, so here's a list of all the major relationships for students, right? It's related to department through majors in, through section and enrolls in, and courses. Well, it is also related to course, right? Through this, student can jump to sections and sections to courses. So somehow it's related to the course as well. So we need to identify inadequate relationships. Here's an example of an inadequate relationship. Okay. Now, this relationship is not in the original class diagram. Okay. This is kind of like a what if. All right. What if, right? When we read this requirements, right, and it said something like student enrolls in courses. Yes? Right? And somewhere else, we might have read that a course has many sections. Yes? Right? Well, it's not too crazy to think that this is the class diagram that we might have drawn, right? Notice that it reads perfectly. The student enrolls in course. Actually, they can enroll in many courses, right? So a student can enroll in many courses, and the course can have many students enrolled in it. Yes? The other relationship that we came up with was that a course has many sections. One course has many sections. Okay? But what I want to talk about is why did we not do this, right? But we could have totally done this, right? We were just lucky not to do this. Right? So what's so wrong about this class diagram, right? We're going to say that this class diagram is an inadequate class diagram. Now, the only reason this is an inadequate class diagram is because in the requirements, one of the requirements was that student declare the current enrolls in that students are going to enroll in sections, right? They can enroll in sections for a course, right? Meaning you, for instance, you as a student, if you go to your Canvas, you can see in your dashboard the courses that you are enrolled and which section. I notice I have two sections here. So some of you are in one section, the other ones are in another section. And if you go to your Canvas, you can see all the sections that you are enrolled. Okay, not necessarily the course, you are enrolled in a section for that course, right? So one of the fundamental things that you want to be able to do in a database is to retrieve the fact, given a student, what sections are they enrolled in? Yes? Or if I give you a section, what students are enrolled in that section? Right? It's kind of the equivalent question. Well, you cannot answer that question using this diagram. This diagram doesn't allow you to answer that question. This diagram says that the students are enrolled in a course, right? But it doesn't say anything about the section, right? This might be students from section 1 and section 2 and section 3 all enroll in the same course, okay? But nowhere are we capturing here what student is in what section and what section is for each student. This says that these sections are for this course, but notice that there's no relationship between a student and a section. So we cannot answer that question, what students are in what section. Okay, so in that sense, this will not do, right? This diagram doesn't work for us, okay? So the requirements say whether a diagram is adequate or not adequate, right? It's the type of questions that we might have asked at the beginning. Okay, imagine that when you enrolled, there were it showed what course you're in, but it doesn't show anywhere which section that you should come to, right? But the sections are at different times. How would you know, right? To go at one time or another time. Yes. Now this is very common in database design. And in databases in general, and computer science in general, right, that requirements change over time. And something that was adequate before, right, because the requirements changed, now the implementation is not adequate, right? And you find yourself having to refactor the implementation based on the new requirements, or maybe a misunderstanding of the requirements, right? This is a constant in software engineering, right? And it will haunt you your whole career, right? Requirements are going to change, and you're going to kick yourself and say, if I knew that requirement, I would have implemented this in a different way, right? If you would have told me this a year ago, I would have done this, okay? And this will haunt you all your career. It is a constant. So yeah, so we want to try, as much as possible to remove inadequate relationships, right? So we need to exhaustively visit, right, all the paths looking for things that are inadequate. Right? So for instance, let's see. Here's another one, right? The student is receiving grades. But we can't answer the question for what section or for what course was this that you received this grade. Imagine you had a list of grades, but it doesn't say what section. You don't know what you got in web dev. You don't know what you got in databases, right? You just say, oh, you got an A here, you got an A, B minus, but I'm not going to tell you which course, what section. And this is exactly what's happening. It says that student is receiving these grades and they're being assigned by this professor, but nowhere does it say that this grade is for a particular section. This tells you this says which sections that you're enrolled in, but it doesn't say anywhere, what grade you got in that particular section. See that? Same thing with the professor. It's assigning grades, but it doesn't say for which section. So both of these are inadequate relationships. We need to fix this, okay? All right, so how do we fix this? Or why did we even do this? How do we get into this conundrum, right? And the reason we messed up, right, is that when we might have read the requirements wrong, okay, which happens all the time. Okay, so here we read this a little bit too literally, right? It says student receives grades. That's what the requirement says. And indeed, we have that. Student receives grades, okay? But if we would have read this a little more carefully, we would have realized that this relationship was actually embedded, right, in a context, okay? So the student receives a grade for an enrolled section. Okay, that this receiving of a grade is within a particular context of a section. Okay, in this diagram, would it be better to add a major class as well? Major class. I'm not sure what you mean. Major class. You mean like a major and a minor? Like you can graduate into the major in the department. Actually, we do, right? We have the, yeah, we will explore that when you might have not just a student can be in one department, but it can be in multiple departments. Yes, we will explore that in a minute. Oh, there was something else in the chat. Could we say student receives grade for enrolled course instead of section? Yes, you could say for enrolled course. Now, the thing is that you miss out on saying that the professor, right, was teaching that particular section and who gave you that grade. If it's with a course, there might be multiple professors teaching that same course. So you miss out on that. You also want to be able to answer the question and say, well, who gave me the A, right? So it's better to be on the section as opposed to the course. All right, so let's revisit this. So why did this happen, right? This has happened because we missed out on the context in which this relationship exists, right? So same thing here, right? When the professor assigns a grade, right, we were a little bit too literal and missed out on the fact that this is a verb phrase instead of just this simple sentence, right? It's in the context of the section, okay? So we want to be able to fix this, right? Instead of just considering two nouns, we need to consider that there might be more than two nouns in the relationship, right? Instead of saying the student receives a grade, right, we want to say that a student receives a grade in a particular section. So let's look at this. Let's look at this one first, right? We have the student receives a grade. Okay. So this two-way relationship actually should be a three-way relationship. A many-to-many between student and section, but then also a grade. And a grade might be maybe like an enumerated data type, like A minus, right? B plus, B minus, C plus, C minus, like an enumerated data type, right? And it might say that, if you give me a combination of a student enrolled in a section, I'll tell you what grade they got. Okay, and in UML, this is perfectly fine, right? You can absolutely draw something like this, but more often, right, you stay away from these dots over here, right? So what does that even mean? How do you implement that dot? Certainly, you can't implement that in a relational database. How would you implement that dot, right? You would need to reify it. You would need to replace that relationship with something more concrete. Okay, how do you implement that? Well, the way we're going to implement it is with a table that has a mapping table that says, which student is is associated with which section, right? So we are replacing one many-to-many with two one-to-manys. See that? Two one-to-manys with the many-to-many, right, on the mapping table, and the ones on the original classes. Yes. In addition to that, right, well, obviously the implementation of this would be that these would be foreign keys pointing to the student and pointing to the section. And then here we're going to have a separate pointer to the grade that this student in that section, the combination of student and section, you got that grade. But that student enrolled in that section is going to get that grade. Okay. So this is the implementation, right, that now allows us to capture the fact that you got this particular grade in that particular section. Okay. So yeah, so we went from this conceptual diagram of student, section, and grade to a reified version of this. Okay. Yeah, so reification basically is making something concrete so that it can be implemented in a relational database, right? All right, so yeah, so we went from this grade class, right, that didn't really tell us what grade did you get for what section, into this reified that is referencing the student, is referencing the section, and is referencing the grade, right? Now we can do the same thing for the professor. Since we can also add here the fact that who gave you that grade. The grade was given to that by this professor. So we can point to the professor and say, oh, that professor gave you that grade to that student in this section, right? And all these are foreign keys pointing to each one of those tables. Make sense? All right, so that's the idea of getting rid of inadequate relationships. Okay, let's take a look at redundant relationships. So redundant relationships, again, is that we want to identify cases that you might be able to answer the same exact question in two different ways, right? And we want to avoid that, right? You want to avoid the fact that if you do a select statement, right, that you ask, what was our revenue last year? And your query comes up to say, oh yeah, we made $1 million last year. Now you make another query which logically is the same query, right? But it uses a different set of tables. It does some aggregation and computation, right? And logically it should be the same, but it comes back with a different answer and says, no, you only made $900,000, right, or $1.2 million. It says, wait a minute, which one is it? Is it one or the other? Logically, it should be the same. Why are they not? Well, you want to avoid even allowing making that in two different questions, right? There should be only one way that the data is represented and no other. There should only be one way that the data is stored. Okay, so we want to eliminate redundancies. Okay. All right, so for instance, let's look at a couple examples of redundant relationships that we already have in our class diagram. So let's see. So here's a question, here's a query. Say all sections a student is enrolled in. Okay. Excuse me. So all the sections that a student is enrolled in. Well, if you look at the diagram, you can answer that question in two ways, right? All the students enrolled in a section, right? So all the students, that's the question, right? All the sections a student is enrolled in, meaning give me a student. Can you tell me all the sections that student is enrolled in? Well, yes, right? I have a many-to-many right here. I can answer that question right here. But because I have this grade assignment, okay, I can answer it also by joining these three tables, right? Because this grade points to the section and it points to the student. So I could, given a student, I could find, following this over here, which sections that particular student is enrolled in. See that? So I can answer this question in two different ways, right? Meaning there is redundancy. Okay, and And we want to avoid that because redundancy breeds inconsistency, right? So here's another one, right? Say we want to find out, what professor assigned a grade. Well, there's two ways, right? The grade assignment is a table that has a foreign key to the professor. So I can know what grade, remember this is pointing to a grade, right? This is pointing to a grade. So this is pointing to a professor. So we can find out who gave you that grade. But another way that you can find out is from the grade assignment to the section. And if we assume that there's only one professor per section, right? If you know the section, you know the professor, you have a foreign key to the professor who taught that section. Well, you can also find out who gave you that grade by navigating from the section to the professor, and now you know who gave you that grade. Right? So this assigns over here is also redundant. You have to keep one or the other. You should not keep both. Sometimes you cannot remove it, right? But most of the times you can. So in this case, you can either keep these two or keep this one, right? About who gave you the grade. All right, so in this case, we're going to remove this assigns, right, as being a redundant, right? So having done that, right, we can remove those redundancies. Wait, no, here. We come up with the following diagram, right? We're removing the assigns over here, and we remove the enrolls over here, because here we can go this way, right, as opposed to this way. And over here, we can go this way to find the professor as opposed to going this way, right? You can answer those two questions easily. Okay? All right, so that's redundant relationship. We want to remove redundant relationships. Okay, so let's get back to something that one of you folks was asking before. What if you had students be able to enroll in more than one section? Wait a minute. Why is this not showing? Okay, you still see my screen, right? So right now we have the following implementation, right? We have one student can enroll in one department, and that's it. Okay. What if we want to allow students to enroll in more than one department, right? For instance, we might have many to many, like this. Okay. And so one student can be in many departments, and the department can have many students, right? Where maybe you have a major and a minor, right? So what would that entail? Well, the way you would implement it, right, is that you would have to reify it. Right? You would have to convert this many to many, which is conceptually fine as a diagram, but because we want to be able to think in both places at the same time as tables and classes, right, we convert this line, we convert it into a table or class, right? We convert a single many to many, we convert it into two one-to-manys, right? Two one-to-manys. Okay, great, that's easy. But what if now we want to be able to keep track of the GPA, right? And your performance in your department, right? What is your GPA? Now, if you just have one major, then that GPA will be just one, right? The student can have the references to the major that they're enrolled in, and also the GPA would be part of the data that you can start from the student. But if the student is instead being able to enroll in multiple departments, well, we would need to also maintain multiple majors, right? Not just one. Okay, but this class doesn't allow us to answer the question for what what is your major GPA for a particular department, right? We can't answer that. We just say, well, these are all your GPAs. We don't know for which departments, right? You got a 3.8 in one department, you got a 3.6 in another department. We don't know which ones though, right? So this class diagram doesn't answer that question, right? Instead, you would need to make a three-way relationship between departments, students, and the grade that you got for that GPA, right? This three-way relationship, okay? Now, obviously, this cannot be implemented in a relational database, so we need to reify this, right? We need to convert this into something that can be implemented. So for instance, we implemented with an additional class or table that is going to have foreign keys. So I'm going to point to the student and the department, right? It says that that student in that department has this specific GPA. If you give them the combination of student and department, there it is, okay? Now, what if you're not even enrolled in the department? Maybe the university allows you to, stay undecided, right, for the first semester or maybe even the first year, right? So meaning that the foreign key over here of the student might not even be referencing a department, right? Maybe you're not even enrolled in the department. So your foreign key is null, right? It's not referencing any records in the department. Well, if that's the case, then you should not have a major GPA either. There is no GPA to speak of, right? Because you haven't decided for the major, right? So just like this is optional and you don't have any foreign keys to that department, you would not have a foreign key in references to the major GPA. Yes? Well, what if, I mean, how would you capture this, right? How would you enforce, for instance, how would you enforce that you don't have, you're not enrolled in a department, and if you're not enrolled in a department, well, you should not have a major GPA. But this diagram here is not allowing us to enforce that. It would be totally fine if the student ID has a record associated with the GPA without having been enrolled in any department, which makes no sense. But this diagram allows you to do that, something that is inconsistent, right? This would allow me to totally have a not null foreign key that points to some GPA, but having at the same time a null that is not pointing to any department, right? This diagram doesn't stop me from doing that, right? So to make this more explicit, so that you only get a GPA if you are in a department, right? We can make it more explicit by using this diagram, right? We could have an additional table here or class that might exist and might not exist, okay? That if you are pointing to it, the student over here, if you're that you are enrolled, then you have a reference to a record, right? Or not, right? This is optional. But if you do, then you have a record that points to the department and it points to the GPA, right? If the student is not enrolled, this would not exist, and so the department would not exist, and the major GPA would not exist, right? So this is one way of enforcing, right, that those two records only exist if some other record exists. Make sense? Anyway, wait a minute. Okay, let's talk about attributes versus classes, right? So we talked about inadequate relationships. We talked about redundant relationships, right? Also many relationships, right? How to encode that. Let's talk about also attributes and classes, right? Now, attributes and classes, so that means basically, the boxes are the classes, and the attributes are what are contained in the classes. Yes. So, for instance, if you have a user, the attributes might be first name, last name, username, password, email, whatever, phone number. So those are the attributes of the user. Yes. Now, obviously, because we live in a society and we are part of the same culture, we might all agree that a user class naturally has attributes: first name, last name, email, phone, blah, 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 blah. Yes? Imagine not knowing that. Imagine that, these are all nouns. User is a noun. First name is a noun, right? Username is a noun. Last name is a noun. Password is a noun. Imagine not knowing that naturally certain attributes are very naturally describe a class. Yes? I know it's hard to imagine, right? Because it's such a common sense thing. But imagine you were talking about you were implementing an application or database about which you knew nothing about the topic, right? Imagine, I mean, I don't know if you know about anything about chemistry or physics or anything. Imagine implementing a database, right, about elements or atomic elements and their composition and the quantum physics and blah blah blah, and you knew nothing about a particular vocabulary, right, or a particular topic, and for you see all these nouns and you don't know how they're related. So you could totally imagine not knowing, right, a whole bunch of nouns and how they're related to one another, right? So the same. So try to extrapolate that into my example of not knowing that the class user has attributes: first name, last name, email, and username. Yes? If you don't know this, then for you, every noun is the same as any other noun. Yes? So you might at first decide that, hey, everything for me is a class. I don't know what is an attribute of something else. So you might start off by, in your initial diagram, everything's a class. Everything's a class, right? Now, as you learn about the nouns and you learn more about the topic, you realize that, say, oh, it makes no sense to have a user class and a first name class. Obviously, the first name class should have been an attribute of the user class. Yes? Right? So this happens, this does happen, that we might have decided that certain things were classes when they really should have been attributes, or vice versa. We thought that certain things were attributes when they really should have been classes. Yes? So let's look at an example, right, of how is it that we do this? How do we convert certain attributes to classes or vice versa? For instance, there's a couple things here. There's a couple of classes: license plate, car model, right? If you learn more about how the university is using these, you might come to the conclusion that, why are these even tables or classes? These could be just attributes of the permit. The permit could just, because you have one permit is for one student and they can only drive that one car, well, that permit could just have the license plate right inside of the permit. We don't need a table for that, right, to list all the license plate. No, the license plate can just live in the permit. Same thing for the car model. I could just say, it's a Toyota, it's a Ford, whatever, right, and put it in the permit instead of being its own class. Make sense? So that's an easy example, right? This one too, year, right? Do we really want a table of enumerated years? Well, maybe that may be useful, right? Because we could totally use that like for a drop down. That'd be very useful. Okay. But you might start asking the questions of saying, well, couldn't this be just a field in the student, or maybe a field in the section, or even grade? Do we even need grade to be a separate table, right? Maybe grade could be just a field inside of the grade assignment, right? A column over there, right? Or even our professors, right? Are professors important enough that they get their own class? Well, maybe. I'd like to think so, that I'm important enough that I get my own class, right? But if you are capturing enough information about a professor, maybe obviously their first and last name, what is their office, right? Although today I guess nobody has an office, everybody's working from home. Whether they're tenured, right? Their date of birth, when they were hired, blah 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 blah. So if you're capturing a lot of fields about a professor, then yes, it makes sense to have a class. And you list all the events. Did it say anything about professors having anything, right? At most, professors were described as maybe a username, and that's it, a username. If that's the only field how we are capturing the idea of a professor, then maybe we don't need a whole table for that. It could just be a field in the section table, right, that says this professor is the one who's teaching this section, and that's it. So So you are the owner of this, right? On how is it that you want to model this, right? So yeah, so definitely license plate can, and the make of the car can go in the permit, right? Also the professor, right, perhaps could be just a username and that's it. Okay. So how do we convert a class diagram that had classes, convert them into attributes? How do we do that? Well, here's a little algorithm to do that, right? So if we have a class C that we want to convert into an attribute, basically we need to make sure that all the other classes that I am associated with are going to get a new attribute, right? So for instance, if I'm going to change year into student and year into section, well, I'm going to need a new attribute in section called year and a new attribute in student also called year. Okay. Same thing here. Grade is associated to grade assignment, right? So I'm going to remove the class. I'm going to need a field called grade where I'm going to capture that information. So we're going to do that. And then once we do that, we can safely just remove the class from the class diagram. And so if we apply that, if you remove year, you remove professor, you remove grade, remove these car model and license plate, and we put them in their parent class, right? Right, so the grade and the professor, what do you end up with? You end up with the class diagram, the very first class diagram we took a look at, early on, at the beginning of the week, right? The student, the section, the enroll, the course, department, and permit. Basically, the same class diagram that we introduced earlier, right? So yeah, so now there might be attributes. There might be attributes that were not even listed in the requirements, right? Things that the owner or the folks who were describing the problem to us, might have not even mentioned them. Maybe they thought they were obvious, right? That there were implied attributes, right? So for instance, for the student, nobody said that students have names, right? Well, because they might have not said it because it's so obvious that everybody has a name, right? So it might not even show up in the requirement, right? And but nevertheless, you have to do the due diligence of making sure that attributes are in there, even though they are not specifically mentioned, right? So you might add to the student, you might add first name, last name, middle initial, right? Same thing here. Maybe nobody mentioned that departments have a name, but absolutely we need a department name, right? So we add that. Maybe nobody added the fact that courses have titles, right? So we add a title field, right? So if we do that, we might add some obvious or assumed attributes. So here they are: student name, department name, the title, right? Also, you're right, it might have not been listed there explicitly, the cardinality of certain attributes or certain classes. We need to go back and make sure that they're listed there, right? That there might be only one professor that teaches a particular section. Okay. All right. I think I'm going to leave it here. Yeah, I'm going to leave it here, and then we'll continue and finish up the aggregation composition when we come back on Tuesday. Okay. All right. Any questions? Remember, what we're trying to do here is that we want to be able to design databases at the class level, at the conceptual level, but always having in the back of our mind that we are going to implement this, right? So we design it in the class diagram, but we know that we're going to implement it as a relational model or relational database. One thing, when I say relational model, okay, wait a minute, what a question, chat. The quiz next week is available until Saturday at midnight. Yes, yeah, all those will be available till midnight for 2 days.
Is there a time limit on the quiz once we start?
Yeah, they're 30 minutes.
I think you cut out there.
30 minutes. The quizzes will be 30 minutes, and usually there's going to be about 5 to 7 questions.
All right, thank you.
Yeah. Yeah. So just one word about the world. These terms are somewhat overloaded when we say relational model. When we say relational, right? Usually we mean that we're going to implement something using a relational database, right? And we know why it's called relational, right? It's because you have all these tables that contain records, and the records are related to one another, right, by foreign keys, primary keys, right? And so we call it a relational database. And then we say that we're going to implement a relational model, right? But the word model, we mean that it has a broader meaning. Means that we want to have a conceptual representation of some physical phenomenon, right? Some conceptual set of ideas that accurately predict or accurately describe some physical phenomenon. So for instance, in engineering, engineers, they model the world or their particular industries through the use of equations, right, or functions, right? So if, for instance, an electrical engineer might model a circuit by having a diagram of that circuit and understanding the laws of physics of the relationships between voltage, current, and resistance, right? And so with those equations, they can describe the behavior of this circuit, right, to some accuracy, or chemists might use chemical formulas of atoms and molecules and whatnot, and describe some physical phenomenon through a graphical representation. Us in computer science, the way we model the real world or phenomena is through these kinds of diagrams, right? We represent some reality using these conceptual representations, and we call this is a model of which we can ask questions, right? We can try to virtually represent something that hopefully accurately represents a real life phenomenon. So when we say a relational model, we mean the set of tables and foreign keys and primary keys and attributes and columns, right, that are describing some set of data that we want to capture that for some business, right, for some role. There's a question. Sorry, can you clarify again? Is it the strong side with the foreign key? No, the weak side has a foreign key. Or weak side, yeah. So in this case, for instance, the student on the weak side, right? That's where the asterisk is. That's where you're going to have the foreign key pointing to the primary key, where you have the strong side. So the strong side has the primary key. So this student has both a primary key, right, with a 1, and has a foreign key, right, to this department. This department doesn't have any foreign keys. It only has a primary key that is being referenced by both. The student is referencing the department, and the course is also referencing the department. Yes? Okay. Yeah, so when I say relational model, I always mean the set of tables and columns and their data types, right? And when I mean schema, also it's an overloaded term. When I mean schema is just basically the structure of data, how the data is structured. And we can represent a schema either using a class diagram. So this class diagram here is a schema. It is telling us how we're breaking up the data into multiple classes. Or the schema can be represented in a relational model, the set of tables and attributes and whatnot, right? That's the schema implemented with a relational database, right? So we might say relational schema, okay? All right, just some jargon there. All right, that's all I have for you today. Any other questions?
Yeah, could you go back to the attribute cardinality slide?
Where?
Yeah, just the attribute cardinality. So is that so? For an attribute to have multiple values, how would we conceptualize that on a table?
You would have maybe an array, a string array, where
Okay.
you might have multiple multiple professors. And if the only thing that you're capturing is the username of the professors, then it could be just a string array, right? If instead the professor is a whole class, meaning it's a whole table, right? Then it would be an array of professors.
So multi-valued attribute would be just having an array of attributes.
That would be the implementation. Yes.
All right, cool. Thank you.
Yep. All right, everyone. Thank you. Have a great weekend.
You too.
Take
Hey,
care.
may I ask something? Real
Sure.
quick?
What's up?
I had written a question, but I don't think you saw it. So if we wanted to add a semester to check all classes available and the graduation of a student, would you recommend adding that semester as a string as an attribute or as a class? Like, as we want to be able to check specific lectures given that semester, I think we should add it as a class. Am I right?
So it depends, right? So if semester is the only thing that you're capturing is, say, spring 21, right? And that's all you need, then it could be an enumerated data type, right? That from which somebody can just have a foreign key to that enumerated data type, or it could be just a field as a varchar in a column in a bigger class. If you want to capture other things about a spring, right? Maybe you say that during the spring semester you can only see level 1 courses or something, where you want to add other things to the fact that is spring semester, right? So and there are certain things about the spring semester, right? Whether you're going to have when does the spring vacation starts, whatever, I don't know, any other information about the semester, then it would be a separate class with its own record, with its own set of fields.
Okay, thank you for clarification. Yeah. Thanks a lot. Have a nice weekend.
All right,
thank you.
I have a quick question about something someone asked on Piazza.
Go ahead.
It was kind of about just knowing Java and JavaScript. I didn't ask that question, but I am also someone who is very unfamiliar with that.
Yeah. So there will be a 1 week after the midterm where we will be doing some Java coding, where we're going to learn how to interact with the database using Java. We're going to query the database and retrieve records from the database and display them somehow. And we will obviously cover it in class, and as always, right, we will do some code ourselves, right? Give you an example and then say, okay, now you do it. Having seen what we did, now on your own do implement something on your own, right? So definitely we will cover everything you'll need to know.
Do you recommend, like, I know you posted like a little link with like a beginner's thing for Java and JavaScript. Do you recommend like I start doing that now? Or
if you haven't done any coding whatsoever, I would absolutely cover some of the very basic stuff. But at this point, I think most students have at least taken a look at Fundies 1 and might
I took Fundies 1 and then I switched to a DS minor. So okay. I'm now taking like Data Science 2000 and learning Python.
Yeah. All right. So if you're familiar with Python, you should totally feel comfortable with Java.
Okay.
And we'll give you everything. If you're familiar with any programming language, you should feel okay with Java, and we'll give you everything you need.
Okay. Thank you so much. I appreciate it.
All right. Take care. Have a great weekend.
Have a nice weekend.
You too. Bye.
All right, goodbye.